Welcome to Algebra 2, Unit 1, Lessons 1 and 2. So what I did was I combined from our textbook, which is completely housed online. I took Unit 1, Lessons 1 and 2 and merged them together into one lesson that I hope will be condensed and easily accessible. Now, if you were in class, you should have a copy of the outline of the notes. If you are not in class, this is pretty much going to give you everything that we went over in class. You want to watch it, do your best at the homework. Everything should be posted online, and you can grab the outline when you come back to class. So without further ado, let's take a look at this. So this lesson is on transformations on functions, and this is not actually in the outline, but I didn't want to hit you guys with like the title of the lesson. If I'm looking to the side, it's because I'm looking at the notes over there. But it says transformations on functions, and it says the goal is to overview the different ways we transform functions. But if you're not sure what that means, like to transform a function, then we're kind of behind at the get-go. So the first question you might ask yourself is, what is a transformation? So a transformation is a movement or change to the position or orientation of a graph. It's actually a little bit more than that. There are like categories of transformations, and we kind of dance around between two of them. But pretty much what we're talking about is you've got some kind of graph on the coordinate plane, and you're going to alter that graph by moving the position. So you're going to move it left or right. You're going to move it up and down. Maybe you're going to flip it over. And then the other type of transformation is we might stretch it or compress it, but we keep the fidelity of the original shape, okay? And so when we're studying transformations, what we're looking for is a pattern between what we do to the equation and then how that shows up on the graph. So examples are, and then what I've got here is the math word, and then maybe like the everyday word that might make more sense to you. So the first kind is a translation. That's just a fancy math word for sliding a graph. So you've got a graph on the coordinate plane and you slide it around on the coordinate plane. A reflection is a flip, and we will study mostly when we're doing transformations, two types of reflections, but there is a third one that comes up when we study inverses. It's got another kind of symmetry to it. A dilation, which is making something bigger or smaller, and that can take a lot of different forms. So if you study that in geometry, it's going to be a little bit different than what we're talking about. For us, it's more like taking the graph and you're stretching it up or you're pushing it down. And then a rotation or a turn, we do not cover those in Algebra 2, but they still fall under the same heading of transformations. So what we're talking about here, when we're talking about transformations of functions, what is this lesson on? We're talking about a graph, and we're going to move or shift, slide, reflect, change the position of that graph on the coordinate plane in some way. So some key vocabulary, and you will find throughout the year, I'm really big on vocabulary, because if you're not sure what the words mean, that will hinder everything from understanding what I'm saying to correctly reading instructions. So there could be a question on a test, the SAT, a final, that is a really simple question, and we don't want the reason that you get it wrong to be because you don't know the words in it, if this is actually a pretty simple thing to do. So the parent function, and I don't want the laser pointer, I want the pen. The parent function is basically, I'm going to try to do this with my hand, the simplest function in a family. Okay, and so it's the simplest, most basic function that falls under the heading of whatever family we're talking about. Now, we kind of open up a can of worms. What's a family? Okay, great. Simplest function in a family. What's a family? A family of functions is a group of functions that share key traits. So examples of families would include lines. So in Algebra 1, you hopefully did a lot with lines, but all lines fall under that family of function called lines. Parabolas, which you should have at least touched on in Algebra 1, those are the graphs of quadratics. They look like little bowls. We're going to study them in Algebra 2 as well. But all parabolas fall under the family of parabolas. And then today's example, which is an absolute value function. And so the absolute value function could be written like this. Whoops, not like that. Sorry, I got distracted. There's a thunderstorm outside, and also my phone just lit up. So y equals the absolute value of x, or you might see f of x is equal to the absolute value of x. Okay, and that's the simplest function that you can have inside that family of functions. Now, if I'm totally honest, absolute value functions don't really turn up in a lot of places. We study them in Algebra 2. After Algebra 2, you will see them occasionally. But one of the things absolute value functions are really good for or about is that they're the graph for them is very, very clear cut. And so when we're studying transformations for the first time, the absolute value graph is going to be one of the easier ones for us to look at. Okay. I wanted to say a word because we have that notation flip there. When I was in Algebra 1, so back in the dark ages when I was in middle school, it was like 8th grade, I think, when I took Algebra 1, we only used y. I never saw f of x notation until I took Algebra 2. And when I learned it, I hated it because I thought I could do everything perfectly fine with y's. Why do they have to put in this new notation that said f of x and it looks like multiplication? It's super confusing. I didn't like it at all. It took me a very long time to really appreciate what that notation is. So a lot of students have been told that f of x is just another way of writing y. And I would say that is mostly true. You can take an f of x anytime you want. If you don't like f of x, you can replace the f of x with a y. It will not compromise the integrity of the problem and what you're doing. But you cannot take any old y and replace it with an f of x. Okay, it doesn't work the other way. Now, a lot of times you can, but there are times when you can't. So what I have here is a little bit of an explanation. F of x, so you do read that f of x. Okay, we might go into that in a future lesson, but I am assuming you've heard that before, is another way to write y that also conveys that the relation is a function. Not all relations are functions. Only if the relation is a function can you do that swap out. Okay, so if you see f of x, it doesn't just mean that it's a relation. It means it's a really specific kind of relation, meaning it passes that vertical line test. Okay, that means that for every x, there's only one y that's going to match up with it. If you were to make a table and you have like x is equal to 3, there is only one y value that is going to go with x equals 3. You're not going to get more than one y value. It also allows us to see both numbers in the ordered pair at once. So one disadvantage of using the x and the y is that you can see what you're plugging in for x, but you can't see y at the same time. When you use function notation, you're able to see both numbers at once, which I thought I had. There we go. For instance, if you saw f of 2 equals 3, what that means is x is equal to 2 because you're plugging in the 2 where the x was, and that is equal to 3, which is your y, since f of x is itself y. So x is equal to 2, y is equal to 3, and so you've got that point on the graph, the point 2, 3. Function notation allows you to see both of those at the same time. All right, where x and y separately, you can only see one. So that is actually material that is not in the notes outline. So if you're watching this on the video, you're actually getting a little bit more than what I would do in class. There should be some trade-off for maybe missing class and having to watch the video instead. All right, so what I have here is I do have Desmos embedded in the PowerPoint. Now, this can be dodgy. Like, I would say this works in class about 60% of the time, and 40% of the time it doesn't work and I have to scramble. When I click on it in this PowerPoint, it changes. You guys can't tell, but it changed everything I can see on my computer screen right now. All right, so what we're going to do is click on this, and we're going to look at the parent graph. So the parent graph is just the graph of the parent function. And in your notes, I have a space for you to just sketch the graph. So I'm going to use y equals, and then there's a couple different ways you can do absolute value. If you look at this keyboard here, if you look down at the lower left, and I expand that, you will see a button here for absolute value, and I can plug in the X, and ta-da. Okay. You can also do this by typing in the letters A, B, S, and then putting the X in parentheses. And you'll notice that the red graph and the blue graph are right on top of each other because you can only see the blue one. That's because it covered it up. I typically, when I'm teaching, I will put the absolute value symbol up there because I think it's easier for you guys to see it. If I just need to graph something quickly on my own, it's actually quicker for me to type ABS than to go into that menu. You can also type your parent function using f of x. Okay, and Desmos will work with that as well. So now we're all the way up to green. Okay, so you can see what the parent graph looks like. So if you're taking notes, make sure that you sketch that down. We often say absolute value looks like a V shape. And you can look at the ordered pairs. So the 0.00 would be on it. And one thing I like about Desmos is if I click on the, if I click on the graph and slide it around, you can see the point. And we are not limited to pretty points like 0, 0. We have all the ugly points in there as well. But you can see that, I don't know if I could be able to get it to stop at the right spot. 2 point. Nope, I jumped over it. But we should be able to see the 0.33. If I come over here to the other side, you notice that the x is negative, but the y is still positive, but the values are still the same. Right? So that's what the parent graph looks like. Okay, I've got to be really careful with how I do this. Because there's a thing I can do. If I click in the wrong spot when I'm in this mode, it will kick me to the next slide and it messes up the recording. I'm sure I will do it a bunch of times. So I'm going to start by looking at a vertical translation or a vertical slide. And in the upper left, you'll see the notation. It's f of x plus k. Now that is a very generic notation. And what that means is take the original function and then add this k value to it. Notice that the addition is outside of the original function. So it's a little bit easier to make sense of that notation with the context of an example. So y equals, remember our parent was the absolute value of x, and then I have this plus 3 on the outside. Okay, and so it's outside of that original function. And then the other example that I have up there, and the reason I'm not using the laser pointer is because I'm honestly afraid of clicking in the wrong space. So we have the absolute value of x, and then we have this minus 5. Now, you could also think of that as plus negative 5, okay? Now, to explore the transformations, what I'm going to do is I'm going to start by putting the parent function, because if we want to see how a function is moving, we want to be able to see where we're starting from. So the red function there is the parent function, and now I'm going to type in the next function, which is the absolute value of x, and now I have to kick myself out of the absolute value before I do the plus 3. And what's great about a graphing utility is that you're able to look at this and see what's happening. So when I added the plus 3, what I would encourage you to do is look at the vertex of the, look at the vertex, and you can see that the vertex went from 0, 0 up to 0.03. And so what that did was it slid the graph up 3 units. Try not to look at like, oh, well, it looks like it's skinnier. It's not skinnier. The only reason it looks that way is because you kind of pushed it up. So the skinnier part is higher up on the graph. So kind of look at that vertex and see what the vertex is. Now I'm going to take a look at absolute value of x minus 5. And again, I need to kick myself out of the absolute value and to be able to see it, and I have to minimize my keypad. But what you can see is that when I subtracted the 5, I actually took that parent graph and I slid it down 5 units. Now, what I usually do in class is I will just start messing around with this, or I'll let you guys mess around with it. I'll say, hey, pull this up on your laptops, pull up Desmos, and I want you to just plug in different numbers. And you can plug in other numbers. So we could do -4, -2, -10. Okay, it kicks it off the bottom of the screen. You can do decimals. So you could try plus 1.5. Okay, and it will slide it up like 1.5 blocks. So you want to kind of play around with that. But what you want to see with this is that adding or subtracting a number outside of the original function takes the function and slides it up or down. So if I can click on the right thing, I have over here, if it's positive, then it's going to slide up. If it's a subtraction or a negative, it is going to slide down. And again, that's the outside number. Okay, that brings us to the next one, which is a horizontal or side to side. And we have that first piece, that notation. Now, I debated like whether or not I wanted to like keep it as like a plus, but the convention is that when you're doing this one, you use a minus. If you think a minus is opposite, that might something's going to make sense in a hot second. But notation is f of x minus h. Now notice that the subtraction here is inside the function. It's inside. So instead of that plus k that was outside, now we have this h, and the h is tucked inside the f, okay, the function. So again, maybe easier for you to see with an example than with the generic notation. I know it would be for me. So in this case, we have y equals absolute value of x plus 4. But instead of that plus 4 being outside of the absolute value, now we put the plus 4 inside the absolute value. Or the next one, y equals x minus 3, and it's inside instead of outside. So if I click on the graphing calculator, once again, I'm going to start with that parent function. Okay, if I want to see where I'm going, it helps to see where I've been. So we'll have x plus 4. And what you'll notice is that my graph, my red graph, which is the parent, went 4 units to the left. Now I want you to slow down. I'll stop talking for a second because I want that to sink in. Plus 4 went left. It is backwards from what you probably thought that it was going to be, because you think, oh, adding should go in the positive direction. Seems like it would. But remember I said earlier, you got like that x minus h, and there's like a negative in there. That's the piece of what's happening here. Now, we don't need to go into the why so much, but you do need to know that adding is going to make it go to the left instead of the right. Will you maybe mess that up once in a while? Yep. Just you got to keep practicing. And if you mess it up, you get the correction, make the correction, and we move on from there. If adding made it go to the left, then most people will think, okay, well then subtracting probably means it goes to the right. And it did. Okay, so our horizontal translation, or sliding them back and forth this way, is inside. So you got adding and subtracting, which can have an outside or inside. Outside is up and down. Inside is going to be left and right. And inside is backwards from what you probably expected to be. So in your notes, you can write, if it's positive, it actually goes left. And if it's negative, it goes right. And what I would do maybe is star that, highlight it. I would do something to that to make sure that I got that, because that is one of the most common mistakes students make, is like that left and right, because it is what we would call counterintuitive. It's not what you expect it to be. All right, make sure I turn off the pen. And we'll come over to the next one. Next one is a reflection over the x-axis. So the x-axis is our horizontal axis. So what we're talking about here is we would flip it over the x-axis. So the notation for this is negative f of x. And you have a note there. Note that the negative is outside of the original function. Okay, so if the original function was y equals the absolute value of x, we're talking about putting an absolute value, or the negative, in front of the absolute value outside of it, as opposed to inside of it, which is something that you will look at for your homework. Taking a look at this, once again, I'm going to throw in that parent function. And the first one is just taking the parent function and flipping it over. Okay, so we have negative absolute value of x, and I'll minimize the keyboard so you can see what's happening there. Okay, and so we take the red function and we're flipping it over the x-axis, so the x-axis is like acting as our mirror. Now the next one combines some transformations, which we will look at in a little bit, but I guess this is the first one where we'll combine them. But we have like x plus 3, and then we also have that flipping over. So from about 3 minutes ago, the x plus 3 means we're going to slide the graph to the left 3, and then we flip it over. Okay, and so we could make a little prediction as to what we think that will look like. And I will minimize this so you can see it. So you actually have two transformations. You've got a slide, and then you have this flip. Okay, so it is like over 3 to the left and then flipped over. But that negative on the outside is what flips it over. Now there is a reflection over the y-axis, and there's a reason why I don't spend a whole lot of time on it, but I did put a couple of exploration questions in your homework where you're pretty much going to do what I'm doing here, opening up Desmos and then taking a look at what that is, because I promise you it's going to do something kind of weird. Okay, all right. So we have sliding it up and down, sliding it left and right, reflecting it over the x-axis. Last transformation that we're going to look at is a vertical stretch and compression. Now there is also a horizontal stretch and compression that is not very common for you to see. Okay, I taught college algebra for years. I did not have to cover it in a college algebra class. So because the stretching and the compressing is much more challenging for a lot of students to see it, I don't want to complicate it by like introducing two different kinds. And what makes it even worse is like a vertical stretch looks like a horizontal compression. And there are ways that you can like rewrite your functions, and yeah, you can just mess around with it. So yeah, so we're going to leave it with vertical stretching and compressing. Now the generic notation there says a, and then it has f of x. That is a times f of x. So this is when you're multiplying the function by some number. And we've got two example numbers there. We have the 2, and then we have a 0.3. And so we're going to explore what that does, and then you'll notice you have a couple notes off to the side. So as always, we're going to start by throwing that parent function in there. If you feel like it, you can time how long it takes me to put it in there. It doesn't take that much time, and it can really help. So let's see what happens when we multiply that function by 2. So y equals 2 times the absolute value of x. And what you might notice, I'll often ask students, like, how would you describe this? And they'll say things like it got narrow or it got skinny. What that is a stretch. And I don't actually have a hair elastic right now. I got a roll of tape. This is probably not going to work. Don't have anything that would work. But the vertical stretch, it's like you take the roll of tape or the function graph or whatever, and you're pulling it upward. And if I pull this vertically really hard, you can see that the roll of tape gets like what we might call skinny. Okay, so picture that like you're multiplying it by 2, and it's like you're multiplying the height by 2. You're just going to stretch it out vertically like so. That's your vertical stretch. Now, if I try the 0.3, what you can see here, a lot of students would say, oh, it got wide, or it got flatter, or it got fat, okay? And that's a vertical compression. So you want to think, again, vertically, like we're doing this up and down, and it's like somebody took the graph and just pushed it down. And when I push it down vertically like that from top to bottom, you can see that my roll of tape gets wide. Okay, it gets like fat. And so we have a vertical stretch when I'm pulling it up like vertically. So we're doing up and down, and then vertical compression, which is that pushing it down. Now, again, you can also do this horizontally, like you can try to pull it this way, and it's going to look very similar to when you push it and compress it that way, and it's just kind of complicated. So this is all we're going to do, like for now in this class, is stretching and compressing vertically. How can you tell which one of those things is going to happen? Excellent question. If the number you're multiplying by is greater than 1, then it will stretch it. Okay, it's going to make it skinny. If the number that you are multiplying by is less than 1, then it will compress. Now, as you're taking your notes, that is the word compress. If you are not sure what those symbols mean, then you need to put the words in, okay? That is greater than, that is less than. And now, most of the time, you are also allowed to use Desmos. So if you blank out, you can plug in the numbers. You can do like pick a number and just try something and see what it shows you and build up your confidence that way. Whoa, that was lightning. But I don't hear any thunder. There's the thunder. Not loud enough for the computer to pick it up, I don't think. Okay, so usually we will see more than one transformation at a time. So what are the transformations to go from the parent function to y equals -3 times the absolute value of x plus 4 minus 2? That's a mouthful. Okay, so I meant to put some animations in here. So what I want you to do, if you're doing this from home, pause the video. I want you to try to list them on your own. Okay, hint, there are 4 of them. There are actually 4 different transformations that are going on. And then if you can't get it then, hint, try graphing it on Desmos if you are unsure. What we'll do in class is I'm going to give you guys some time to work on this, and then we'll share it, okay? But for those of you following along at home, pause the video and do it now. Okay, so what I'm going to do here is do it out on the graphing calculator, and you can check your answers and see if you're right. Now, as always, if I want to see the transformations, it is a good idea to put the parent function on there. Now I'll graph the new one. So I have -3. And then in my absolute value, I have x plus 4. And then I have to kick out the absolute value, -2. Now, I like to do these going from left to right. So I am going to hazard turning on the laser pointer so that I can point. So the first thing I notice as I go from left to right is I have this negative out in front, and we explored that, and hopefully you've got your notes handy. You can go back and look at it if you want to. But a negative out in front flips it over the x-axis. And when I look at my graph here, I can see, yep, that flipped over the x-axis. I am multiplying by a 3. Well, 3 is greater than 1, so that is going to stretch it out. Now, somebody is going to ask me in class, I hope, or you're thinking at home, but wait a minute, Miss Taylor, -3 is less than 1. So it should have not flipped it over, and it should have made it really compressed or really wide. Yeah, sort of. You're on the right track, but the way we have to process this is like the negative and the numerical value do two different things. So to be really, really precise about it, on the previous slide, I should have said if the absolute value of x is greater than 1 or the absolute value of x is less than 1. And the reason I don't do that is because to introduce this other absolute value in the middle of an absolute value function is like verbal soup. So it's a little bit easier just to conceptualize that as the negative is going to flip it over, and then the 3 is going to stretch it out. The +4 on the inside number is the left and the right. And it's backwards from what you expect. So you expect positive, it should go right, but then you remember, I don't like that's backwards. Positive means it goes left. Okay, so we have it flipped over, we have it skinny. If I go 1, 2, 3, 4, it's gone 4 left, and then the -2 on the outside brings it down 2. And so you want to keep your eye on that vertex. Okay, on a test question, what I might do is I might give you a function like this and say state the transformations. You may or may not be allowed to use Desmos, so you want to be able to do it either way. And then I would give you like a point for each transformation that you've got correct. So if you feel good about the up and down and about the flipping, then give me the up and down, give me the flipping, and then guess at the stretching and compressing. Okay, do what you need to do. Okay, turn off the laser pointer. We are almost done. So with your table mates, I guess if you're doing this at home with your table mates, but I want you to answer this question or consider this question. You start at y equals negative the absolute value of x plus 3, and you want to go to y equals the absolute value of x plus 5. Okay, so what makes this one different is that you're not starting with the parent function. You're actually starting at one spot and you want to move over to some other spot. What transformations are needed to go from one to the other? Be prepared to share your ideas with the class. So if you're doing this from home, I want you to pause the video. You can open up Desmos, do whatever you need to do, and try to figure out the answer to this question, and then unpause the video and I will go over it. Alrighty, so hopefully you did that. So let's take a look at this. So for this one, instead of starting with the parent function, I am going to start with this function for wherever it is that I wanted to start, which is negative absolute value of x plus 3. So where I'm starting is in a flipped over position and 3 to the left. Okay, and I want to go to y equals the absolute value of x plus 5. And there we go. Okay, so we're starting at the red one and we want to get to the blue one. So the question is, how do I get there? Well, I need to flip it over the x-axis. Basically, I need to unflip what had been flipped. We got to flip it back. So we're going to need to flip it over. And then if you keep your eye on that vertex, I need to go, so I'm going to flip it over and I need to go 2 to the left. So your answer to this question would be reflected over the x-axis and go 2 to the left. For most of you, it is going to be easier for you to see that than it is to just get it from the functions itself. Now, if you don't have access to Desmos, what you would probably do is you would by hand do a quick sketch of the first one. So let me turn on the pen and I'll show you what I mean by that. So what you would do is you would take that first one and you would, whoa, sorry, I got something on my desk there. You would do something like this. You'd say, okay, it's 3 to the left and it's flipped over. And you do a really quick graph like that. And then you'd say the second one is 5 to the left. And it wouldn't be perfect. It would literally be just as fast as what I did. And then you would have your picture and be able to go from there. But the answer that you should have come up with is flip over the x-axis and left 2. All right, so the last problem here is an application problem. And this is just to get an idea of like how you might transform actual functions. So the scenario here is you design a computer game. Your revenue in dollars for X downloads is R of X equals 2X. Your profit is $50 less than 90% of the revenue. What is the profit for 100 downloads? So that's a lot of vocabulary, and it's a lot of mathy sounding vocabulary that we've got in there. So we're going to break it down. You'll notice that I have over to the left, I have key vocab, because one of the things that can happen in a word problem is that you can understand the math and you get tripped up because you don't know the context of it. And so you don't know where to put the math into the problem that you have. Always be aware when you need to ask that question. Okay, so I might give you a homework problem and your question might be, Ms. Taylor, I don't know what this word means. So I'm going to define these for you really simply. Revenue is the amount of money you take in. Okay, it's how much, when you are selling your computer game, how much money you're actually taking in. Now, if you look at the function over here, R just stands for revenue. So another advantage to that function notation is that you can name your functions whatever you want. So if you've got a problem with multiple equations in it, you can actually give them a name. So R just means revenue. Okay, it's literally all it is. And revenue is 2 times X. What that means is that you're charging $2 for people to download your game. Okay, so for every game you download, you are going to intake $2. Now, your profit is going to be a different number. Your profit is, I'm going to define this again simply, the money you take home. Okay, because you don't take home all of your revenue. If you own a business, you probably have to lease a building, you have to pay your employees, maybe you have to pay for like a software thing that you use, you have to pay an app store to advertise your game, like you've got stuff that money that you gotta go out. So you're gonna bring all this money in, but some of it is gonna go out to your business expenses. Your profit is what you have left over when all of that is done. So the revenue is the money you take in. The profit is the money you're actually taking home. So you don't have to pay it out. So now that we know what the vocab means here, it says your profit is $50 less than 90% of the revenue. Now, where you might get tripped up on this is you can see there's 2 different things that are going on here. $50 less probably means you subtract 50. Okay. And then 90% of the revenue is kind of like finding a tip in a restaurant. If you're going to tip 20%, you have to do 20% of the bill. So it's like an operation you have to carry out. So finding 90% of the revenue is something you need to carry out. It's an operation. So we need to have a strategy here. So the strategy, we're going to find 90% of the revenue. Okay, 90% of the revenue. And then once we know what 90% of the revenue is, the profit is $50 less than that. So then we will subtract the 50. Now, the actual question is, what is the profit for 100 downloads? So X is the number of downloads. So we will plug in 100 for X. Now I want you to notice some of the things that I did there. I did circle like the key pieces of information. I actually wrote out what my strategy was going to be. And that's super helpful for me as your teacher, because if you write down your strategy and then you make a mistake executing it, I can go back and find that, or I can kind of get a sense of, okay, what were you trying to do? Where was the direction you were going to go? Now, before we do the revenue, like the 90% of the revenue, I am going to do like a little side lesson here for a second. I taught middle school for 4 years, and I know that this can be a sore spot. If you are looking for percent, okay, I'm going to actually write the word percent over here. The piece of the word cent, C-E-N-T, literally that means 100. Now, if you're like, huh, what do you mean? Think about how many cents are in a dollar. Okay, we're using dollars. You got pennies. How many cents are in a dollar? 100. How many years are in a century? That would be 100. Okay, so C-E-N-T, and if you speak another language, like I studied French in school, and cent, C-E-N-T, is literally the word for 100. Spanish, I know, is similar. Okay, so there's a lot of like word connections you can make there. So percent literally means per 100. So 90% literally means 90 out of 100. That is literally what that symbol and the word means. It means per 100 or out of 100. We use this all the time in education, because if I say, oh, you got 31 out of 35 points, the first thing you want to know is, well, what percent is that? And because it gives us a nice means for comparison. Okay, so if you want to find 90% of 100, what you would do, or 90% of 100, 90% of the revenue is you would take 90%, which is 90 over 100, and multiply that by your revenue. Now, I'm going to try to simplify this a little bit. 90 over 100 is not the friendliest fraction. So what we will often do is we will change that over to a decimal, just because it's easier. You can do that on Desmos, okay? Or you might just know what it is. It is 0.9. And then we're going to multiply that by the revenue function, which is 2x. There's our 90% of the revenue. Now we will subtract 50. Now, you can plug in the 100 right now, okay? That would work. Or you can simplify that first part, and you can do like 0.9 times 2, which would give you 1.8x minus 50. There is some flexibility with that, okay? Like what you want to do. So you could, you could plug in the 100 right away. Now the actual question, now that's the transformations part, is multiplying by the 0.9 and then subtracting the 50. So what you're doing is you're compressing it and moving it down. So you're gonna smush it down, and then slide it down 50 units on the coordinate plane. Now, to solve the actual problem, we're going to go ahead and plug in the 100. And it turns out 100 is a nice thing to multiply by. That's going to give me 180 minus 50, or $130. So if you get 100 downloads, the money you're actually going to take home is $130. Right? And that just gives you an idea of how you can carry out these problems, like the transformations, like what they might look like in an equation. This kind of problem, we probably would not approach it with graphing. You can tell on this slide, I didn't open up Desmos at all. Not to say that you couldn't. Okay, but it's an option, and it does show you that, and we get a nice little review of percents and such. All right, I think I put one more slide in here. Homework, there's a worksheet. It should be due next class. I actually lost track of how long this video was, so I'm not sure, what we're going to have for time in class. So if you're not sure, send me an email, but I'll make sure that I get like the video uploaded and the homework uploaded and that sort of thing, so you have the resources you need. Thank you for watching. If you have questions, you know where to reach me, and hopefully I will see you in class soon.